Ladies and gentlemen, welcome to the 12th Peter Lindsay Memorial Lecture. There are many past and present students who have reason to be most grateful to Peter Lindsay, after whom this lecture is named. For in a very generous bequest, he specified that a significant portion was to be used to help students who found themselves through no fault of their own, in financial difficulties. Happily for us this evening, Peter made it possible for the Department of Electrical and Electronic Engineering to organize an annual lecture. If you have not heard of Peter Lindsay before, his fascinating background is to be found in the brochure that you've been given. Our speaker this evening is Professor Chris Bishop, who is a laboratory director at Microsoft Cambridge and Professor of Computing Science at Edinburgh University. He's well known for his expertise in artificial intelligence, which of course everybody's interested in nowadays, and it's the subject of this evening's lecture. Since his biography is also in the brochure, I'll waste none of his time by repeating it and invite him to present the 12th Peter Lindsay Memorial Lecture. Yes.
Artificial intelligence, as you obviously all realize, has become the subject of intense interest over the last few years. We've seen governments and big tech companies investing literally billions of dollars into research in artificial intelligence, and it sometimes seems that you'd be hard-pressed to find a startup that doesn't claim to be using AI in some way. But it's also been the subject of some fairly dire and scary predictions. Here are some recently published books that tell us that will artificial intelligence save us or destroy us? Superintelligence, paths, dangers, and strategies. Artificial intelligence and the end of the human era. So what's really going on? Well, in this lecture, I want to peel away all the hype and tell you about what's really happening in artificial intelligence. And it has nothing to do, in my view, with the end of humanity. But there is a very exciting story to be told. It's not the one that's usually told. Artificial intelligence can be thought of as a very legitimate scientific quest to see if we can create in machines all of the extraordinary capabilities of the human mind. Now, in the last few years, we've made some rather specific and rather spectacular progress in certain aspects of that quest. However, in my view, unless there's some breakthrough in the very near future, we are a very long way from Turing's dream of 7 decades ago of having in machines all of the capabilities of the human brain. So does that mean that all of this huge investment, all of this excitement is a waste of time? I don't think so, because there is something happening which I think is truly revolutionary, but it's not yet full artificial intelligence. It's something rather different. Let me explain what I think is going on by an analogy. So in technology, there are two components. There's the hardware and the software. And I want to begin by looking at the history of computer hardware. Now, it goes back a very long way, certainly at least as far as the work of Charles Babbage and the analytical engine, the differential engine. These were very early types of computer built out of brass gear wheels, which was the state-of-the-art technology of its day. His ideas were a little bit ahead of their time, and these never really worked, but conceptually they were brilliant, and they were forerunners of modern computers. Things got a whole lot better with the development of thermionic valves, or vacuum tubes, as they'd be called in the US, and these allowed the first modern-style computers to be built. They were fast, and they were practical. However, they were expensive, they were unreliable, they consumed a lot of power, and a real breakthrough came with the development of the transistor, much smaller, much more efficient in terms of its use of energy, much cheaper, and much more reliable. And things continued to get better. People learned how to integrate multiple transistors onto a single piece of silicon to produce logic gates. The logic gates became ever more complicated. Finally, we ended up with processors of the kind that you might have found in your personal computer a few years ago. Very fast, very powerful, relatively very cheap. And that trend continues, and today the state-of-the-art in computing consists of data centers, enormous aircraft hangar-sized buildings full of thousands and thousands of processors, storage, networking, all delivering incredible processing power. So the history of computer hardware, as you know, is one of the hardware becoming faster, cheaper, more reliable, more capable. But the key thing to understand is that this progression has not been uniform. There was a very specific piece of technology which changed everything. Prior to that piece of technology, the progression is what you might loosely call linear. Beyond that, it became exponential. And that critical breakthrough technology is called photolithography. And it changed everything because up to that time, if you wanted to build a computer, you first of all manufactured all the components, and then you joined the components together to make the computer. The components might be gear wheels, they might be vacuum tubes, they might be transistors, they might be logic gates. Here you do something very different. The process of photolithography is very much like the process of printing. On a wafer, perhaps 12 inches across, you print dozens of microprocessors all at once in effectively a single step. It might be 30 steps or 50 steps, but it's a small, finite number of steps, and it's a constant number. There's a constant amount of effort to fill that wafer with transistors, with microprocessors. And then what happened is the transistors became smaller. As the technology improved, the transistors became smaller, and it became possible to pack more of them onto a wafer of silicon. So think about printing a sheet of paper. If it costs a penny to print a sheet of paper, then as you make the font size smaller and you put more letters onto the page, the cost per letter goes down. So as you make the transistors smaller, you fit more of them onto the silicon, they get cheaper. But something else happens as well. These transistors, when they get smaller, they can switch on and off faster, and so the computer gets better. So here's a piece of technology which, as it got better, got cheaper. Right? Usually, if you want a faster car, you have to pay more money. But here, there's a technology that's working in the other direction. And what's really profound about this is that the number of transistors that can be packed onto a given area of silicon roughly doubled about every couple of years. And that's gone down in history as Moore's Law, named after Gordon Moore, who was the founder of Intel. And that doubling every couple of years held for many decades. That's what we call exponential growth. And that changed everything. The reason we have all these technology companies, the internet, the reason that you're carrying a supercomputer in your pocket has everything to do with Moore's Law, to do this exponential growth in the capabilities of computers, which is qualitatively very different from the roughly linear growth that we saw prior to that time. So that's the reason Moore's Law, Moore's Law enabled by photolithography is really what underpins the digital revolution. Now, it's my belief that we are at a similar inflection point in software. The history of software goes right back to Ada Lovelace, who was the world's first software developer, and she wrote software for Babbage's analytical engine. Now, she had to specify this software at the lowest possible level. She had to specify where every gear wheel was and its exact positions and so on. So it was very slow and very time-consuming to produce that software. Since then, the productivity of software developers has increased dramatically over the years. Software developers today are much more effective, they're much more efficient, they produce much more code in a given amount of time. That code is much more capable, it's much more reliable. Today we have things like integrated development environments in which a software developer can draw upon the work done by thousands of other developers, add more to it themselves, and in a very short time produce very sophisticated software. But in a way, what the modern software developer does is not so different from what Ada Lovelace was doing. The modern software developer effectively is telling the computer what to do at every step. They might make a high-level command, bring up an orange window in this position, and they use some code written by somebody else to tell the system how to do that, and that calls other code that perhaps was written semi-automatically by a compiler, all the way down to some machine code that tells every transistor how to switch on and off. So a modern software developer is still telling the computer how to solve the problem. What we're seeing now, underpinning the excitement around so-called artificial intelligence, is really a revolution in the way software gets created. So this revolution is called machine learning, and it's a profound change because instead of telling the computer how to solve the problem, we do something very different. We write very different kind of software. We write software that allows the computer to learn from experience, and then afterwards we train the computer to solve the problem by using data, by using examples. And you can tell that it's profoundly different because the software that's used to enable the computer to learn is often quite generic. We'll look at some technology called neural networks a little bit later. These neural networks can be used for a whole host of different problems in speech recognition or speech synthesis or computer vision, natural language understanding, a whole range of different domains. It's very flexible and very general. Now, why do I think this is a profound transformation? Well, it's a profound transformation because the thing that limits traditional software development fundamentally is the intellectual capability of the human mind. It's the ability of the software developer to hold a certain amount of complexity in their heads. It's the ability of that software developer to dream up an algorithm, a set of instructions which will cause the computer to solve a particular task. Now, if it's adding up a column of numbers, that's pretty easy, but if it's recognizing somebody's face, it's extremely hard. In fact, it turns out many of those tasks are impossible. People have tried for many years to write down a set of rules that would recognize handwriting or interpret speech, and almost without exception, it's been a complete failure. So now we have a different approach based on teaching the machine through examples, teaching the machine through data, and so now the thing which limits the capabilities of machines becomes the data. And what's really interesting is that the amount of data in the world is growing exponentially. In fact, it's doubling, roughly speaking, every couple of years, just like the number of transistors on a silicon chip. So if you believe that we're at an inflection point, if you believe this is a revolution in the way we create technology, if you believe that it's limited by data, if you believe the amount of data is growing exponentially, doubling every 2 years, and likely to continue to grow exponentially for many years to come, then perhaps we're seeing an inflection point in software that could be as profound and as revolutionary as photolithography was in computer hardware. So I think that's the reason why artificial intelligence today is a very exciting technology. So the next question is, well, how can a machine learn? Well, the early inspiration for building machines that could learn in the way the brain learns really comes from our understanding of how the brain works. Now, we don't really know how the brain works, but we know something about the brain. Here's a cross-section of neocortex, the evolutionarily most recent part of the brain, the sort of convoluted outer layer of the brain. You see various layers of cells. These cells are called neurons. They're electrically active. A small number of them have been stained in this cross-section. And what you see is this tremendous complexity, this network of fibers all interconnecting. And roughly speaking, what's going on is this. We have these electrically active cells called neurons, and a neuron can fire. It can create an electrical pulse, and the electrical pulse travels down the fiber called the axon. And at the end, the axon branches, and it makes connections to other neurons. Those little connections are called synapses. And if a neuron receives enough stimulation from other neurons through its synapses, then it too can fire. And some of those synapses also can inhibit the cell from firing. So when a signal arrives at a particular synapse, it can prevent the cell from firing. So what we have is a very complex network of these cells. When I say complex, the number of neurons in your brain is roughly the same as the number of trees in the Amazon rainforest. But what's interesting is not the neurons, it's the connections between them. Because the synapses are adaptive, they're plastic, they can change based on experience. And it's the synapses, we believe, that are largely responsible for the ability of our brains to learn. And each neuron makes tens of thousands of synapses with other neurons. So the number of synapses in your brain is roughly the same as the number of leaves on the trees of the Amazon rainforest. And that's why we say the brain is by far the most complex object in the known universe. So this is Frank Rosenblatt, and back in the 50s, late 50s, early 60s, he built machines that were inspired by that superficial level of understanding of how the brain works. He built artificial neural networks called perceptrons. And in those days, there were very few digital computers, so he built an analog computer to implement his idea of a perceptron. And one of the remarkable things about the perceptron, it wasn't just a sort of an ad hoc idea, something he threw together one afternoon. It had a theoretical basis. He showed, mathematically, that if his perceptron could learn the solution to a problem, if there existed a solution, then his perceptron was guaranteed to find the solution, and it was guaranteed to do so in a finite number of steps. Of course, there was a catch. I'll come on to the catch later, but first of all, let's just have a look at the perceptron and how it works. So this is the input to the perceptron. It's an array of cadmium sulfide photocells, and you can think of this like a very primitive, very, very slow digital camera. So each of those pixels is like a light-sensitive resistor, and that provided the input to the perceptron. And he would train the perceptron to do tasks like telling the difference between a triangle and a circle. And so here you see the setup. In this case, it's obviously trying to tell the difference between different letters of the alphabet. There's some very powerful lights shining on the target here because the camera was very insensitive. There's a big lens, and inside this box would be that array of sensors. And then the data from the sensors will be sent into the perceptron. And this is really the heart of the perceptron. These things, each of these, corresponds to a single synapse. It's an electrical motor driving a rotary resistor or potentiometer. And so depending on the electrical signal sent to the motor, it could move the resistor, and when the power is switched off, that resistor would have a particular position. So the value of that resistance corresponds to the strength of that synapse. And there was a very particular procedure corresponding to his mathematical algorithm by which the perceptron would respond to the stimuli it was given and would adjust the positions of all these potentiometers. And essentially what would happen is, let's say you wanted to distinguish a circle from a square, you would show it an example of a circle, and then you would tell it this is a circle. And its output would either say circle or square, and if it got it right, it was fine. If it got it wrong, you made a small change to all of the synapses so that the output became more likely to be correct. And then you show an example of a circle and tell it this is a circle, and so on. And you repeat this many, many times, showing it lots of examples. And sometimes, after a finite number of steps, it would converge and it could learn the solution. And not only could it learn the solution, I mean, that itself was pretty amazing, but it had lots of other amazing properties. Here's one of them. This is the wiring of the perceptron, and if it looks like it's wired up at random, that's because it was wired up at random. And why was it wired up at random? He was trying to make a point that unlike a conventional computer, where you have to wire it up very precisely, you could have random internal wiring, and it would simply learn how to effectively unscramble that and produce the correct answer. Not only that, you could go in with after it's trained, you could go in with a pair of wire cutters, cut 10% of the wires, and it would still work. Not quite as accurately, but it would still work. We call that graceful degradation. It's a property that our brains exhibit, which is fortunate because if you go and have a few pints of beer, you're killing off some extra neurons, but your brains still work. Not quite as well as they did the day before, but nevertheless it carries on working. So all of this generated a tremendous amount of excitement and buzz back in the day. But there was a bit of a problem, and the problem was that it didn't always work. And so it was a mystery. Sometimes it worked well, sometimes it didn't work at all. And then other mathematicians came along and analyzed this more carefully, and they discovered that the perceptron has some very serious limitations. It's very restricted in the set of problems that it can solve. And people essentially lost interest. And so we saw the first wave of excitement around neural networks, and then we saw them go away again. And this has been the history of this subject. So those were perceptrons. People lost interest again. And then there was another development. So the development has to do with the idea of layers, and I'll say a little bit more about this in a moment. But the reason the perceptron was so limited is that it had only one layer of adjustable parameters, only one layer of adaptive processing. And that's why it was so limited. And in the late 1980s, Jeff Hinton at the University of Toronto and others discovered a way of training neural networks that have more than one layer. And it was a technique, calculus-based technique called backpropagation. And that led to an even bigger wave of excitement around neural networks. In fact, the excitement was so great that it even influenced me. I was a physicist. I'd been working on the fusion program, doing theoretical physics of tokamak instabilities for about 8 years or so, having a fine career as a physicist. And this caught my attention. And I'd never really been interested in computers before because I viewed computers as sort of rather dumb things that do exactly what you tell them, but by doing it very fast, they can do magical things. But this was exciting. This was something very different. The idea of a machine that could learn, a machine that might become intelligent, a machine that was inspired by the brain was very exciting. And I started to apply neural networks to data from fusion experiments. It was the sort of the big data of its day. Had a great time, cleaned up a lot of low-hanging fruit because I was the only person sort of with this non-linear hammer that I could go and attack these problems. And I had so much fun that I actually switched fields, and I've been in the field of machine learning for the last 30 years. Now you'll see it dipped down again. It dipped down again because it turned out that although backpropagation could train networks with many layers, in practice it really only worked if the networks had 2 layers. And networks with 2 layers were pretty good, and they could solve some very useful and practical things, but again, they had their limitations. And so, again, we saw a decline of interest in neural networks, but this time because other better techniques came along. And then, just a few years ago, there was another breakthrough. There's a little set of, coming together of a set of circumstances that I'll explain in a minute, which allowed us to train networks that have many, many layers, these so-called deep neural networks. And this allowed us to have very flexible systems that could tackle much harder problems than were possible previously. So let me just give you a little bit more insight into a perceptron and what it is and what these deep networks are all about. So here's a little schematic of a perceptron. So the X's there are the inputs. In Frank Rosenblatt's perceptron, there'd be the signals from those cadmium sulfide photoresistors. And they're combined together by some adjustable weights, the W's. So the W's are like the synapses in the brain, the potentiometers. And so for those of you who like maths, if you don't like maths, this is about the only equation in the whole talk, but if you like a bit of maths, you know, one equation's worth 1,000 pictures or something. What we do is we take a linear combination of those inputs and then pass them through a function, a nonlinear function, in this case a simple on-off step function. So that's the perceptron, brilliant when they work, but very limited in their capabilities. So a neural network really takes the idea of a perceptron, but instead of having just one output, it has lots of these neurons, and then it processes them layer after layer. So a deep neural network, we have many of these layers. Each layer, again, is just doing that linear combination followed by a nonlinear function. But one of the changes that was made was to replace that step by a smooth function. And the smooth function can be differentiated, and that allows us to use so-called gradient-based methods to tune all the parameters in the network on the basis of the training data. And so it's that use of calculus and gradient-based methods which is really underpins the technique of backpropagation and allowed us to train complex neural networks. So here's one of the classical neural networks that really led to this explosion of interest in the field of machine learning, and in a sense the rebranding of machine learning as artificial intelligence. This is a so-called convolutional neural network. This is fairly close to being the kind of state-of-the-art that you would use for processing images. I don't have time to explain this, but these are blocks of neurons, and each neuron looks at little patches on the previous layer. And this is rather like the way cells in our retina, cells in our LGN and V1 visual cortex, attend to little regions of the retina. And so again, there's some biological inspiration in there, but there's also some very solid engineering. There's some sharing of parameters, so-called convolutional neural networks, and a lot of rich structure. But the end result of all of this is that it achieved a breakthrough. It achieved human-level recognition of objects in images. Now, this is a problem which had been around for decades. The state of the art prior to this was very, very poor for machines. This type of deep neural network allowed us to take very large data sets involving thousands of different categories and classify them with better than human accuracy. Now, I should say that better than human accuracy might be taken with a little pinch of salt. Yes, it's better than humans, but it's also much better at distinguishing between 127 varieties of mushroom than most people are. Nevertheless, these systems have achieved human level and beyond human level accuracy, not just in telling the difference between mushrooms and beef stroganoff, but also in very important problems, for example, diagnosis of cancer. So there's a Nature paper recently looking at using deep neural networks to look at skin lesions and to decide just from images whether those skin lesions are benign or whether they're malignant. We have ground truth because eventually you know whether they turn into cancer or not, or you have a biopsy. And the thing is, the neural network can see far more examples during training than any single dermatologist could ever see in a human lifetime. And that's the state of the art today. There's no reason to imagine that these neural networks, given even more data, given even more layers, given even more processing power, given even more clever ideas on how to structure the network, couldn't carry on improving in performance. But here's the thing, it wasn't just image analysis that was revolutionized. Many other fields were. And the other one that was a really early success was speech recognition. This is actually the founding vice president of Microsoft Research. This is work that was done jointly with University of Toronto, Jeff Hinton's group, and Microsoft Research in the US. And this is a live demonstration of translation into Mandarin. So Rick is giving a talk in English. The voice is being captured as being transcribed into text by a deep neural network with a much higher accuracy than was possible previously. It's then being translated into Mandarin, again using deep neural networks. And then finally, deep neural networks are being used to synthesize his speech in Mandarin, but using samples of his own speech, so it sounds like him, but he's speaking Mandarin. And that produced an extraordinary reaction in the audience. And the real excitement here came from the fact that speech recognition, turning speech into text, had been the subject of enormous research for many decades. But for the previous 10 years, there'd been essentially no progress. Many, many PhDs had been sort of burned up trying to tackle this, lots and lots of ideas, nothing really worked. Along came deep neural networks, and the error rate plummeted. Year after year kept falling. So today, you walk up to a phone machine, you just start talking, it understands what you're saying, you take it for granted. Those of you who remember using speech recognition systems prior to deep neural networks, remember you had to sit there for half an hour in a quiet room with a special microphone dictating so it could learn your particular voice, and even then it didn't work very well. So that's, in my view, the real excitement of AI, this revolution in the way we create technology because of a revolution in the way we write software. But there's a sort of another side to this. So learning from data is at the heart of this revolution, but the yin of the yang, as it were, is that there's another change that follows from this, which is the importance of uncertainty. So in traditional computer science, everything is deterministic, everything is binary, it's 0 or 1. The engineers, the computer scientists go to great trouble to make sure everything is very, very precise. But when we're dealing with the real world, we're dealing with images, we're dealing with speech, we have to deal with a world of uncertainty. And so there's a corresponding transformation in the kind of foundations. The foundations of this modern software technology is very different from traditional computer science. And uncertainty, of course, is everywhere in this world. So thinking about which movie should the user watch next, we don't know for certain which movie the user is going to like the most, but we have some ideas on it. So we have some information, but it's not certain. What word did they write? What did they say? Which page are they trying to find? What they're going to click on? What gesture are they making? What's the prognosis for this patient? And so on. All of these are things where the computer can provide information, but in no case is it absolutely certain. So what we need is a calculus of uncertainty. And it turns out that there is a unique calculus of uncertainty. If you express your belief in whether it's going to rain tomorrow as a number, and if you are rational in the way you manipulate those numbers, then those numbers will behave like probabilities. And so we call them probabilities. And if you're not rational, I'd love to have a game of dice with you afterwards. All right. So probability is something that we all kind of learn in school, and there are really two views of probability, if you like. There's the one that we usually learn, which is probability is the limit of an infinite number of trials. There's a 50-50 chance this coin will land heads. What we mean by that is if we flip the coin many times and measure the fraction of times it lands heads, then in the limit of an infinite number of flips, that fraction will get closer to, in a certain mathematical sense, to a particular number, and that number is 0.5 if it's a fair coin. So that's probability is the limit of an infinite number of trials. We need a much more general view of probability, the so-called Bayesian view, which is the one I talked about already, probability as a quantification of uncertainty. And just to sort of try to illustrate the difference between these two viewpoints, supposing you have a coin, but imagine the coin is bent, so it's not a fair coin, and 60% of the time it'll land concave side upwards, and 40% of the time it lands concave side downwards. And now one side of the coin we'll suppose is heads and the other is tails. And I don't tell you which is which, if I ask you, what is the probability that when I flip this coin I will get heads? Well, what answer should you give? Well, the rational answer is 0.5. It's symmetrical. There's no reason to believe it's anything other than 0.5, but that doesn't mean, that's not the frequency sense, it doesn't mean you believe that if we flip the coin a very large number of times, the fraction of flips that are heads will be 0.5. What you believe, given the information I've given you, is that that fraction will either be 0.6 or it will be 0.4, but you don't know which. So the probability of it landing concave side upwards is a repeatable event, and that probability is like a frequentist probability, but the probability of a particular flip being heads depends upon which side is heads and which is tails. That's not a repeatable event, it's a fact, you just don't happen to know it. And so that 0.5 is a quantification of your uncertainty about which side is heads, which is tails. And the first kind of probability is a special case of the second. So this, and probabilities, of course, are numbers that lie between 0 and 1, or between 0% and 100%. And this seems like a small change, a small difference. After all, conventional computer science is based on binary, it's based on numbers that are 0 or 1, and I'm saying that modern machine learning is based on numbers that lie between 0 and 1, and that seems like a very minor tweak. I want to show you that the difference is quite profound, and I want to do so by showing you something quite remarkable if you've not come across this before. So this is a bus, obviously. There's a car. Now, the bus is longer than the car. There's a bicycle. The car is longer than the bicycle. Now, if the bus is longer than the car and the car is longer than the bicycle, do you agree that the bus is longer than the bicycle? Put your hand up if you agree. Brilliant, most of you agree. There's a few not quite sure. I wonder if there's a trick question. But no, you're a very smart audience. You're absolutely right. That's called the transitivity property. The bus is longer than the car is longer than the bike, therefore the bus is longer than the bike. It's common sense. But we're dealing here with deterministic numbers. When we go to the world of uncertainty, that transitivity property need not apply. And here's a very simple example. These are called Efron dice, or non-transitive dice, and they have the following property. Supposing you, by the way, these are completely fair dice. They're not loaded in any way, just that the choice of numbers on the 6 faces is a bit unusual. And you can see the numbers are, so this one here just has 3s on every face. It always rolls a 3. If you roll the orange one against the red one, then 2/3 of the time, this will produce a bigger number. So the orange will beat the red 2/3 of the time. If you roll the blue against the orange, 2/3 of the time, the blue will produce a bigger number than the orange. If you roll the green against the blue, 2/3 of the time, green will win. And then here's the really bizarre thing. 2/3 of the time, the red will give a bigger number than the green. So it's non-transitive. So now that you know the secret of this, you equip yourself with a set of Efron dice, and you go and have a bet with somebody, and you let them choose whichever one they want, and you play the best of 11 rolls or something. You're very likely to win. Bet them £5. And when they lose, of course, they'll want to play with your die. So you let them play with yours. You just pick the next one in the sequence and carry on. And whichever one they pick, you can pick one that will beat them. And by the time they've wised up to what's happening, you should have paid for a good few pints of beer. And if you're curious to know how they work, this is the answer, and we won't go into it now, but these are things that I sometimes, in my increasingly infrequent spare time, give talks in schools. And one of the things I do is hand out sets of these dice, which our designer rather brilliantly realized you could color them and arrange them to form the Microsoft logo, which I think is rather sweet. And you can go to NT Dice to read about how they work. My point here is simply that this switch from a deterministic world to a world described by probability is again a profound transformation. I have one more equation, but it's if there's only one equation you need to pay attention to, it's this one. It's called Bayes' theorem, and this really is the mathematical basis for modern machine learning. And it was developed by the Reverend Thomas Bayes some 3.5 centuries ago. This might be a picture of Bayes, we don't know, but it's usually shown when people are talking about Bayes' theorem, so I'll follow the tradition and show that picture. This is Bayes' theorem, and Bayes' theorem relates various quantities. So this quantity P of y is called the prior, and it's called the prior because it's the probability, your degree of belief before you've seen some information. So maybe the probability that it's going to rain tomorrow. You may think, well, it's a nice sunny day today, and it's late May, maybe the probability of rain tomorrow is 20%. And Bayes' theorem allows you to calculate the posterior probability. That's the probability after making an observation. So perhaps your observation was a satellite image of the North Atlantic, and you see a great big low depression sweeping in, and you think, oh my goodness, maybe the probability of rain tomorrow is not 20%, maybe it's 80%. So this is a precise mathematical way to take a prior probability and turn it into a posterior probability by incorporating new data. And the relationship between these two is a thing called the likelihood. And a key point here is that this is iterative. So we take our initial probabilities, our initial belief in the world, and we update that belief using Bayes' theorem on the basis of some data, and we get a posterior distribution. That's the revised probability. Now we can incorporate some more data and revise it again. That posterior becomes the prior for the next observation. And so this is what's happening in modern machine learning. We're thinking of the machine itself has an internal representation of the world in which uncertainty is represented by probability. And as the machine sees data, it uses Bayes' theorem to update those probabilities. And as it becomes less uncertain about the world, it's learned something from the data. So that's the general idea. Let me make it concrete by showing you a little demo. And this is a demo of something probably fairly familiar to most of you. What we're going to try to do is recommend a film to watch, recommend a movie to watch. And a real system that's going to recommend a movie to watch will take account of lots of information about the movie, its length, its genre, who the actors were, and so on. And if it knows something about you, perhaps your age, your gender, your geographical location, other information about you, that might also be relevant to working out which movie you'll like. But the purpose of this demo, imagine we know none of that. We don't know anything about the individual movies, and we don't know anything about the individual users. What we do know, though, is that we've got some users who very kindly rated some of the movies for us according to whether they like them or they don't like them. So you can think of this enormous table with perhaps tens of thousands of columns. Each column is a movie, and each row is a person. We might have tens of millions, data from tens of millions of people. And the data simply consists of the following, that a certain person watched a particular movie and they liked that movie, so there's a tick. And then some people watched some other movies and they didn't like those movies, so that's a cross. But this table is very sparsely filled. Most people haven't watched most movies. And so there are a lot of blanks. And what we want to do is fill in the blanks. We want to know, will a person like a movie that they haven't yet seen? Okay, that's the goal. Can we produce a system that will achieve that for us? So what I'm going to show you now is just a little demo that was written just specifically for things like this lecture. But the underlying technology is the technology that's actually used on an industrial scale. So what we have here is just a subset, just 200 movies. And we've taken some publicly available data that was published by Netflix, in which some anonymized users had watched, I think it was about 10 or 20,000 users in this case. Those users, some of the users have watched some of the movies, and what we're going to do is, in this case, we're going to use this system to try to predict which movie I might like to watch. Now, I wasn't one of the people on the Netflix database, so at the moment it knows nothing about me. So first of all, I need to give a little bit of information, and it doesn't know anything about the movies, it doesn't know anything about people, age, gender, and so on. So the information I need to give it is whether I like a movie or not. So let's imagine that I've watched a particular movie. Let's say it's Pretty Woman. What I'll do is I'll drag this across into the green region. So what I'm doing is I'm telling the computer that I've watched Pretty Woman and I like this movie. Okay, what it's doing now is it's rearranging the other movies on the screen in the following way. So the vertical placement of the movie doesn't matter. They're just spread out vertically to make it easier to see. What matters is the horizontal position. And that horizontal position is the probability, according to the machine, that I will like the movie. So if the icon is right down the right-hand side here, then it's very confident that I will like it. If it's hard up against the left-hand side, it's very confident that I won't like it. And if it's in the middle, it's completely unsure, it's 50-50, whether I'll like that movie or not. And what you see at the moment is that it's really pretty unsure what's going on. There's a lot of white space here. There's nothing that it's really confident I'll dislike, and there's nothing really that it's confident I will like. There's a lot of uncertainty because everything is clumped around the middle. And that's not surprising. The only thing it knows about me is I liked the movie Pretty Woman. So I need to give it a little bit more data. So let's pick a movie. There's one. Let's suppose I don't like that. So I'll drag that across to that region. And this machine learning algorithm is just running here on the laptop in real time. And what you saw happen there is the movie spread out sideways. So they started to move towards regions, away from this region of high uncertainty, towards regions of greater certainty. But it's still, it's still fairly uncertain what's going on. Let me give it a little bit more data. Let's give it a couple more examples. So there's one that I like. Here's one that I don't like. And now after just 4 examples, we see a very different pattern emerging. There's now quite a lot of white space down the middle. There's a few movies where it really has no idea if I'm going to like it or not. But there are some down the right-hand side. It's very confident that I'm going to like these movies. It's very confident that I'm going to dislike those movies. What's happening here intuitively is it's looking at my pattern of likes and dislikes based on the 4 ratings that I provided, and it's finding similar patterns of likes and dislikes amongst that population of 10,000 people. And it's assuming that if somebody else in that population has similar likes and dislikes on these 4 movies, that I will share their likes and dislikes on movies that I've not yet seen but which they have seen. So intuitively, that's what's going on. But the key point here is we didn't take that intuition and code it up as an algorithm. That's the old-fashioned way of developing software. Instead, what we code up is effectively Bayes' theorem, and then we teach the machine using data, and that pre-training phase takes a lot of compute and happened, one I prepared earlier, and then it does a little bit of extra Bayes' theorem when I provide the ratings. So it was taught how to do these ratings from examples. And because of Bayes' theorem, it's just sort of, as it were, automatically doing the right thing. So it accords with our intuition, but we didn't code up our intuition, we coded up Bayes' theorem, and then the right things happen. I'm just very quickly going to show you one more thing, because I can't resist, because this demonstration is brilliant for illustrating something that most people learn in sort of first-year electrical engineering degrees, but I can illustrate it very simply here, which is the difference between data and information. Now, if I think about giving a rating, when I say I like a movie or I don't like a movie, I'm providing some data because I'm providing a binary digit, a 0 or a 1. A 1 if I like the movie, a 0 if I don't. So let's take a movie down the right-hand side. So here's a movie. It's very confident that I'm going to like this movie. So let's suppose I watch the movie and, guess what? I do actually like it. So what I've done is I've dragged it across into the green region. I want you to watch very carefully what happens to the movies when I let go of the mouse, right? So here we go. I'll do that again. So I'll pick another one. Here's one. It's very confident that I like this movie. And I say, yes, I do like it. So watch carefully what happens. Tiny change. And that's because there's very little surprise. It's very confident that I'm going to like it. So when I say, yes, I do like it, there's actually very little information in that data. There's very little surprise. So it doesn't learn very much from that data, and so nothing much changes. Now let's take another one. So here's one. It's very confident that I'm going to like this, but supposing I don't like it. So what moves that over here? So watch very carefully what happens when I let go of the mouse. Okay, there's a huge degree of surprise. And Claude Shannon, who invented the field of information theory back in the 1920s or thereabouts, defined information as the degree of surprise. And every rating contains the same amount of data. It's a 0 or 1. But the amount of information goes from 0 at one side. It goes logarithmically to infinity across the other side. So that's the simplest way I know of explaining the difference between data and information. Okay, so there was a simple illustration of this modern view of machine learning, and underpinning it all is this graph. This is not a neural network. It's called a probabilistic graphical model. This is, each of these boxes is called a plate, and it says everything within this box is replicated a certain number of times. So the user box here, there are 10,000 copies of all of these nodes, and messages are being passed around this graph, and that's what Bayes' theorem actually looks like when you represent it for a real-world problem. A little bit more complicated than the equation you saw on the previous slide, but the principle is the same. Okay, so let's look at why now. Why just in the last few years has this field exploded. What's happened? Well, there are really three ingredients in this revolution. The first one is big data. It's the fact I've already explained that the amount of data in the world is growing exponentially. We have, in the last few years, had data sets that are sufficiently large that these neural networks can actually produce good performance. When I was first playing with neural networks 30 years ago, we didn't really realize that the hundreds or thousands of data points that we were training on, that was hopeless. We needed millions or hundreds of millions or billions of data points to get things to work really well. The second one goes hand in hand with that, massive compute power. Again, the machines we had 30 years ago really just weren't up to the task. That's why we had small data sets, because the computers weren't very powerful. Today, we have much more powerful computers. And then finally, improvements in algorithms. And I've mentioned some of those, backpropagation and some of the other breakthroughs in the algorithms. And the combination of these three, which has really caused the field to take off. And then there's been a sort of fourth factor. The fact that we have these successes is causing enormous investment in the field. It's causing a lot of people to move into the field, so a lot more brains thinking about this, a lot more money available, and that's accelerating the flywheel. So why is the amount of data in the world growing exponentially? There are lots of reasons for this. One is that we've understood the value of data. Instead of throwing it away, we're starting to keep it. But also we are developing all kinds of new sources of data. Smart cities, smart cars, instrumenting our bodies. It's remarkable that your car has at least 100 different sensors monitoring its health, and yet your body somehow doesn't seem important enough to bother to monitor. And there are many people who think we ought to do a lot better than that. And so the so-called Internet of Things, intelligent devices, cheap, low-cost devices connected to the Internet are one of the sources of this exponential growth of data. It's estimated there'll be many tens of billions of Internet-connected devices in the coming years. I talked about compute power, and I said how we went through, from brass gear wheels all the way through to data centers. This is a modern data center, Microsoft data center in North America. What you see, if you can see the scale of this is a car park. So there's some cars, and you see these very large buildings. If you were to go into these buildings, you wouldn't see any people. There'd be just rows and rows and rows, racks and racks and racks of compute and storage and networking. If you look at the top of the picture, you'll see there's some building work going on because the data center is being expanded. And if you fly around and look for the other side, you can see it's quite a significant expansion. What we're seeing today is just a massive growth in this exascale compute. So the modern computer is a huge building. And companies like Microsoft and other companies are investing very heavily in so-called cloud computing enabled by these centralized data centers, which bring many advantages. It means as a user or as an application, you can access for a short period of time huge amounts of compute power. Your phone wants to solve a little task. It can send the task up to the data center, and for a fraction of a second, it can access enormous compute power. And then it goes away again. And you couldn't afford to buy that amount of compute power and have it sitting around just for the few seconds a month that you want to use it. But that elasticity, that flexibility is one of the many, many advantages of cloud computing and why it's really, really a big revolution in itself in computing. Now, at this point, I'd love to talk to you about applications. There isn't time. I'm just going to show you this one slide, but there could be a whole lecture in itself of the many, many applications that are currently being developed of machine learning. I'll show you, obviously, I've chosen this example not at random. This is work that's being done in my research laboratory in Cambridge in collaboration with Adam Brooks Hospital. This is Raj Jenner. He's a radiation oncologist. He's our collaborator at Adam Brooks, and we collaborate with other hospitals around the world. And his job is to take people who have cancer, take a three-dimensional MRI or CAT scan image of their tumor, and plan radiation treatment. He's a radiation oncologist. And a key part of his workflow is to take that three-dimensional image and segment out, find the boundary of that tumor in 3 dimensions. Because that information will be used to plan the radiation therapy so that the radiation is targeted at the tumor, causes as much damage as possible to the tumor and as little damage as possible to healthy tissue and especially to vital organs like the eyes, for example. Now, it's a time-consuming and tedious process. You go into hospital today and see how this is done. The oncologist will sit in front of a computer screen and will go slice by slice through this 3D scan, and with a pen, a stylus will mark up the boundary. It's tedious and time-consuming. It can take 20 minutes for a simple tumor. If metastasized into multiple regions, it can be very, very time-consuming. So we've used machine learning to learn what a tumor looks like, learn where the boundary is, and to automate this process. So the segmentation now takes a fraction of a second, and the radiation oncologist then simply has to look through the proposed segmentation, make any little tweaks if they're not happy, and then accept that segmentation, and then it goes on as usual. So it's taking a piece of the radiation oncology workflow that's tedious, quantitative, and time-consuming, and speeding it up and making it more accurate. And so this is being used very much on a research basis, but actually being used in Addenbrooke's and other hospitals. And we're very excited about the potential of this technology. And of course, people like Raj are very excited too, because it frees up their time to do the thing that they most want to be doing, which is thinking about the radiation, planning, to be engaging with the patient, to talk about the options, talk about the risks, and arrive at the right decisions, but decisions which are supported by accurate quantification of the tumour. There are many other applications. If you're looking at a drug trial and you want to see how the tumour is responding, again, the state of the art is just to measure the longest linear line through the tumour and see how that responds, but we can actually measure very quickly the three-dimensional volume and quantify that precisely and see the effect of drugs, for example. I want to close out really by just touching briefly on another topic, which is really the difference between what we can do with technology and what we should do with technology. This is very powerful and very general technology, and like any very powerful and general technology, it can be used for a very broad range of things, not all of which may be desirable. And I'm very proud to say that Microsoft and many other tech companies now have been very much in the forefront of thinking about the ethics of AI, the ethics of machine learning, and trying to find some principles which guide how we should use this technology. So Microsoft's principles are called FATE, Fairness, Accountability, Transparency, and Ethics, and they provide sort of touchstone, high-level guidance in how to think about the best ways to deploy this technology, and also on what occasions perhaps we shouldn't deploy it. How do we put those principles into actions? Well, there's much to be said here. I'll just touch on a few examples. We have a committee called ETHA, which looks at the ethics of AI in engineering and research, and it advises the company on when the technology should be deployed. And it's a powerful committee, and on occasion the company has walked away from opportunities to deploy technology commercially because it's deemed to be inappropriate. Microsoft was also one of the founders of the so-called Partnership on AI. So the Partnership on AI is a collaboration of now more than 80 partners, including many non-profits, working together across the industry to think about the best way to make use of this technology, to try to understand the pitfalls, to anticipate them before we reach them, and then hopefully avoid them. This is a picture of the Microsoft Research Lab in Cambridge, just outside the railway station. And one of the foundations of our approach to artificial intelligence is to be both inclusive and multidisciplinary. So we don't just have people there who are mathematicians or people who specialize in machine learning algorithms. We have plenty of those. We also bring together engineers, we bring together social scientists, designers into multidisciplinary teams, so we can think about how to build effective end-to-end solutions that work in the real world for real people and go beyond just the immediate task of getting the algorithms to work. So I want to finish with one final thought. We began by looking at the risks of AI, super intelligent machines taking over the world. I don't think that's something you should lose any sleep over, at least not for the next few decades. But that doesn't mean the technology isn't without risks. We've seen a few examples of the technology, not with ill intent, I don't think, but perhaps being used in ways that had undesirable outcomes. For example, if you learn from natural data, and that data has biases, gender bias, race bias, whatever it might be, the machine learning can learn the biases, and because the machine learning can be so fast, it can amplify those biases. So it can take a problem and amplify it and make it worse. And the converse is true, of course, as well. If we understand the challenges, then the technology potentially can remove the biases and can actually make better decisions than if left to humans alone. So there are challenges with the technology, but I want to emphasize there are enormous opportunities. As I've mentioned healthcare, because that's an area that I'm particularly interested in, but there are many, many opportunities for this technology to influence all aspects of our lives in ways that we would all very much welcome. But it all depends on data. And data, of course, is something that we need to treat with great respect. And so I'm going to share with you, finally, a project that we've been working on, again, in the Microsoft Research Lab in Cambridge, which is about how we get the best of both worlds. How can we get the benefits of learning from data while also respecting privacy and security that we often need to associate with that data? So this is called multi-party machine learning, and the scenario is we want to combine data from several different sources. Let's say we want to combine medical image scans from multiple different hospitals. But for whatever reason, we don't want to pool the data itself. Perhaps the hospitals don't want to release the data to other hospitals for whatever privacy or security reason. Or this might even be individuals. It might be your individual health records. You'd like your health records to be used to advance medical science. People sometimes say, well, is my data being used for such and such a purpose? It's a reasonable question. I sometimes ask, why isn't my data being used? Why aren't my medical records being used to advance medical science? Because the potential for that is tremendous. Here's a way to combine data and to do so in the cloud. And what's remarkable about this, it's built on something called Azure Confidential Compute that we developed in our lab. And it has the following property. When data is sent to the cloud, of course, to one of these data centers over the internet, it's encrypted. So if somebody intercepts it over the open internet, then it's meaningless. And when it's stored in the data, center, it's also encrypted. So if somebody were to hack into the data center and retrieve the data, it would be just meaningless. But to do something useful on the data, you can't compute on encrypted data. There's some very special circumstances, but in general, you can't compute on encrypted data. You have to decrypt it, and at that point, it becomes vulnerable. And so in Azure Confidential Compute, the decryption happens within the processor itself. So even data flowing on and off the chip to the chip next door on the card, that data is always encrypted. And so even if you were the administrator of the data center, and even if you had all the passwords, and even if you had an oscilloscope and all the time in the world, you could look at the data coming on and off the chip, but it would all be scrambled and meaningless. So you'd have to somehow take the chop of the chip and goodness knows what to get at the data. So this is a situation in which the different providers of the data cannot access each other's data. The cloud provider can't see any of this data. It's all happening or being processed in the chip. But the output is something like a trained neural network, and that trained neural network can be made available to the providers of the data, or again, it can be held securely within an encrypted form, and the providers of the data simply send examples and get back predictions. So that's just one example of how technology can help us address both the challenges and the opportunities of providing and achieving the great benefits that can come from machine learning. So with that, I'll say thank you, and I'm more than happy to take questions if there's time. Thank you.
Professor Bishop has kindly agreed to take questions. If the two people can grab the microphones. Thank you. If you put your hand up, a microphone will come towards you.
Thank you very much for that fascinating talk. And I was just wondering, looking a little bit further ahead, what your thoughts are on a couple of issues relating to the advent of quantum computing and also potential regulatory interference. Do regulators understand enough to be able to be effective in what they're doing?
Yeah, super interesting. So quantum computing is a technology which is, still, for those of you not familiar with quantum computing, it's a radically different approach to computing, which is based on quantum physics. The idea that, a simple way to explain this is a conventional computer uses bits, everything is 0 or 1. In a quantum computer, a quantum bit can be in a superposition of a state of 0 or 1 at the same time. And the point is, if you have two quantum bits, then there are 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. And so there are 4 combinations, and those 2 quantum bits can be in any one of those 4 configurations. Add another quantum bit, it doubles, you get 8. Another one, it gets 16, and so on. And so with fewer than 100 quantum bits, you have more configurations than there are atoms in the universe. And so if you're able to compute over those structures, then potentially you have a computer which is exponentially more powerful than a conventional computer. And for certain tasks, there are algorithms that have been developed, which means for certain tasks which would be prohibitive for a conventional computer to solve, could be solved by a quantum computer very quickly. The challenge is nobody's been able to build a quantum computer. Microsoft has a very interesting approach to this. So lots of people are developing quantum computers, and Microsoft is pouring a lot of resources into quantum computing, but we're looking at this from a very different perspective from everybody else. So a lot of people have, quantum computers with maybe tens of quantum bits. I'm not sure what the current record is, but that number will increase, and as it gets sufficiently big, we'll start to do interesting computation. Microsoft may or may not have a quantum bit. We're not quite sure. It's called a Majorana fermion. There's evidence that it might exist. It's unusual because it's a so-called topological bit. The reason that quantum computers are so hard to build is that these quantum bits are very fragile. Literally, if you look at them, you destroy their coherence. And so they're extremely fragile. A topological quantum bit's a bit like a knot in a piece of string. If you shake the string around, it moves and changes shape. But the fact that there's a knot in the piece of string, the topological property doesn't change. So it's much more robust. And so the hope behind these topological quantum bits is that if they can be built and scaled, they'll produce much more robust quantum computers. So it's a sort of high-risk, high-return bet. It's probably the only option for producing quantum computers with billions of quantum bits, but it's still very much a piece of fundamental physics at this point. The implication of combining them with machine learning is very exciting because there are certain ways in which quantum computing can accelerate machine learning. But actually, even not looking that far ahead, because we don't really know when the first practical quantum computer will come, what we're seeing today is a lot of effort being put into special purpose silicon that enables machine learning. So if I didn't go into detail on this, but I talked about the importance of compute power. In a sense, machine learning researchers were very lucky. We were lucky because the games industry, which is a big business, the games industry have been developing special purpose processors called GPUs, graphical processing units, designed to render images on a screen very, very fast for real-time computer games. And it turns out that the computational operation in a GPU is very much like the computation in a deep neural network. And so machine learning researchers recognized this and took GPUs from the gaming industry and repurposed them to do machine learning. And that was one of the reasons that these breakthroughs in things like object recognition images were possible, because of the existence of this special silicon. What's happening now, of course, is machine learning has become every bit as important or even bigger than the game industry. And so there's a lot of effort being put now into developing new kinds of silicon chip specifically for machine learning. And those are much more powerful than general purpose CPU processors that you'd find in your laptop or your phone. But specifically on machine learning algorithms, they run very, very much faster. And that's a very, very hot area. So we're seeing almost factors of 10 per year increase in the power of computers measured in their ability to run machine learning algorithms. So even before we get to quantum computing, there's a very exciting runway just for the next few years. Sorry, what was the second question?
Just on regulation.
Regulation, oh yes.
Keep up and what are they likely to
Two very different. It's a challenge. I think the regulators recognize that. If you look at GDPR, there are special cases for research that take account of the... I think there's an understanding that we need to be thoughtful about the opportunity as well as be mindful of how we protect data. But I think there's no doubt, I think the world is quite rightly becoming very mindful of privacy, of the importance to secure data. When I think actually of the dangers of machine learning, I tend to think less about the dangers of the technology being misused, because they are, I think, widely studied and widely thought about, which is good. I think there is a risk, though, and perhaps it's through regulation, but it may not be through regulation, but a risk that as a society we shut ourselves off from the opportunities to apply this technology where it can do good. If you think about healthcare systems are just bankrupting the developed countries. The costs are increasing. It's tough in the UK. The US spends about 2.5 times as much per capita as the UK with very similar healthcare outcomes. The costs are increasing all the time. The outcomes are pretty stagnant. The cost alone was just one factor, but the opportunity to have technologies that can, I gave an example of diagnosis. We'd already have technologies that can outperform human experts in diagnoses. The potential of that technology in healthcare is really transformational, but it depends upon, rather like the movie demo example, it depends upon being able to bring together data, for example, across millions of people. We need to do that in a way that derives the benefit but protects the privacy of individuals.
We have time for one short question.
Okay, since it's a short question, first question I have is regarding the IBM, because they've done a quantum computing which you can have access to do some of the algorithms. I was wondering whether you've used any of that for machine learning. And the second thing is, because you were comparing it versus the hype and what's happening, on the Gartner hype cycle for emerging technologies, where is AI?
Yes. I'll answer the second question first. We're probably heading to the trough of disillusionment. I think that's what it's called, isn't it? I don't know that we're quite on the Gartner cycle, in the sense that we've been through several of these cycles before, and the excitement has gone away, but for different reasons each time. This time, I think it's not going to go away. I don't worry that the field of machine learning is going to disappear. It's too useful, it's too valuable. I worry that we will somehow close off, as we were talking in the previous answer, about turn our backs on the opportunities, that maybe through regulation, or it may be just through locking down the data. It may be just those who have the data deciding it's too valuable and hanging on to it. I mean, that's one barrier. But in terms of quantum computing, then real quantum computers at scale don't yet exist, but there are simulators that exist, and Microsoft has one called Liquid, and there are others, and people are starting using those simulators and thinking hard about how quantum computing could be applied to machine learning. There are lots of very interesting opportunities there. But as I said, we don't even before quantum computing arrives, even the trajectory we're on right now is things are not slowing down. There were some developments in natural language towards the end of last year that are quite remarkable, because they used factors of 10 more compute power than had been used before, and new emergent properties arise in these systems that hadn't been seen before. So this is not a field that sort of ran out of steam. It just seems to be accelerating. So I don't know what the next few years hold, but it's going to be an exciting ride, I think.
Okay, thank you. I'd now like to call upon Emeritus Professor Marek Sergot of the Imperial College Department of Computing to propose the vote of thanks.
Thank you. I saw the reference to hype in the title, and I couldn't help thinking about the last wave of AI that we had, the last boom, and how things had changed in the meantime. So these things go in cycle, as the last question alluded. The last boom was in the 80s, fizzled out in the 90s. That followed a winter of AI, following a report that was very critical about the state of AI. I promised myself I wouldn't say this, but I'm going to. I can't help observing that the trough between the last two, the previous boom and this, coincides almost exactly with my own research career. So I just caught the end of it. Then I benefited a bit, and then we had a trough. That was my career, and now we're back in a boom. There are some differences. There are many differences. I don't have time to go through them all. One obvious one is the technology is different. So at the moment, the dominant technology is machine learning and statistical methods of the kind that Chris has outlined for us. Previously, the emphasis was on inference systems, symbolic processing, knowledge-based systems, expert systems, and so on. An example I used to use when teaching was an advert I saw from a computer data agency which said, "Let our expert system match you to your ideal partner." And I used to ask the students to think, if that wasn't mere advertising blurb, what could it possibly mean? If you know what expert systems are, then there was a meaningful answer to that question. These days, the same company or a similar one would say, "Let our advanced machine learning artificial intelligence system match you to your ideal partner." From Chris's talk, if this isn't mere advertising blurb, you probably have quite a good idea of how this system might be constructed. It's not the same. Anyways, I mean, the problem is we don't know whether it's mere advertising blurb or true. Last year, I heard a person being interviewed on the TV who'd connected up various devices in his home, Internet of Things, things like that. In the trough, a mere 2 or 3 years ago, that person would have said, I wrote a program to automate the central heating in my house. What he said now was, I have constructed an artificial intelligence to control the central heating in my house. I don't know whether that person has constructed an artificial intelligence or what even that might mean. I'll leave it for you to dwell on the connotations of what he said. Some of us might have sleepless nights thinking about living in a house or an artificial intelligence, whatever that is, controls where we live. If you watch too many films or read too many books about the future of AI, this is what might frighten you. This isn't what frightens me about the future of AI. What frightens me about the future of AI, I'll explain with the following example. This time last year, a friend, actually a colleague, a person I knew from undergraduate days, now a QC, wrote to me and said, my son and his friend have just finished an MSc. They've had the idea of applying machine learning to financial data and have started up a startup company to market and develop this application. They don't really know what they're doing. They've downloaded a system from the internet and read a book about it, and they've run it through their financial data. Could they come and see you so you could give them some tips about how they could improve it? I was shocked and frightened for more than one reason. He said, I'll buy you a pint when I see you. This was the most frightening and shocking thing, that he thought he could buy my expertise for the price of a pint. He's a QC. I nearly replied, one of my sons has got himself in legal bother. He's developing his own defense. Could he come and see you and get some tips? I'll buy you a pint when I see you. The really frightening thing, though, was that his sons were developing an application which was being marketed as applying advanced AI techniques to the analysis of your financial data. And they don't know what they're doing. And there are thousands of these companies. Some of them know what they're doing, and some of them don't. And I can't tell the difference. I think in this climate, we should be very grateful that there are people like Chris who has the gift and the enthusiasm to explain to us what is really happening and where things are heading. As with all these things, reality is much more interesting than hype. What can actually be done is much more interesting than the science fiction books and the science fiction films, in my opinion. So on behalf of all of us, Chris, thank you so much for taking the time and giving us such an inspiring and illuminating overview and glimpse of your fascinating world. Thank you.